What I want to talk about today was propositional logic. And this is going to seem super abstract at first, but it's really helpful with proving mathematical statements. So let's just get into it. So first, we just take two different statements, right? So we have a statement, it rains, and then another statement, the ground is wet. And what we can do is we can form a compound statement, something like, if it rains, the ground will be wet. And here, we just call this P, statement Q, and here this is saying P implies Q. And what we can do is we can change the truth value of P and Q to true or false, right? So just P by itself is true, and then not P means P is false. So then this is going to be it does not rain, and then not Q is going to be the ground is dry, right? The ground is not wet, the ground is dry. Okay. And then what we can also think about is the overall truth value of this compound statement P implies Q. And we can think about what the truth value of this compound statement looks like when we change the truth values of P and Q. So let's just go ahead and look at this in a sort of table. Okay, so we have P, we have Q, and we have P implies Q, like that. Okay, and right, we're only gonna have four possible combinations of P and Q since P and Q can either be true or false. So the simplest case, when they're both true, we're gonna have P implies Q is true. And then, right, now let's look at when P is false. Now, our P implies Q, this is kind of our operating rule here. And our rule tells us if P is true, then something else must be true. But it says nothing about when P is false. So technically, when we have P is false, we're not violating anything. So our compound statement must be true. So when P is false, Q can either be true or false. The whole compound statement, the whole implication is going to be true because we're not violating our rule up here. But when we have P is true and Q is false, we're directly violating our rule. We say here it says if it rains, the ground is dry, but our rule says if it rains, the ground is wet. So this right here is in direct contrast to our rule up there, so this is going to be false. Okay, so now what we can think about is, okay, like let's play around with some other compound statements, changing the value of P and Q or changing its position. So let's just look at what it would look like for it to be not P implies Q, right? Here this is saying not P implies Q. This is saying if it doesn't rain, the ground is wet. Okay, so first we can look at if P is true, right? Because we automatically know that if P is true, then we don't even touch our rule because our rule only applies for when P is false. So if P is true, right, so here and here, the whole implication is going to be true since we're not violating anything. Okay. Now when P is false and Q is true, this is exactly what our implication is saying over here. So it's going to be true. But then when P is false and Q is false, this is in direct contrast to our rule that says if P is false and Q is true. This is going to be false. Okay, now let's look at one more. Where we can play around this a bunch, but let's look at a particular case where we have not Q implies not P. So I'm gonna get rid of this. So not Q implies not P is saying if the ground is dry, then it did not rain. Okay, so let's go ahead, right, let's look first where Q is true, right, because when Q is true, we know, like from the previous patterns that we've seen, if Q is true, the whole statement has to be true, because we're not violating our rule. So Q is true, these ones, we're gonna have the whole statement has to be true. Now, when Q is false, this implies P is false. This is directly agreeing with our rule here. But when Q is false, here we're saying, this is saying if the ground is dry, then it did rain. This is directly violating our rule that we've established up here. This is going to be false. And now what we can see, the big picture here, is that this column aligns with this column. And what this means is that these two implications are logically equivalent. So what this means is that P implies Q is logically equivalent to not Q, is logically equivalent to not Q implies not P. And why this is important, like the applications to math, is that if we're trying to prove a mathematical statement that says if P implies Q, and it's really, really hard to prove this, we can try looking at, okay, if we can prove that the negation of Q implies the negation of P, then we prove our original statement here. So what logical equivalence allows us to do in the context of mathematical proofs is prove things in a more circuitous way, and it might end up being easier than proving it directly. So we can kind of prove things in a roundabout way that might make it a little easier. Yeah, so this is propositional logic.